the viral because the problem here it's a viral infection. When you talk, we discuss a viral infection that in one patient. One patient, more precisely, the HIV, it's attack the lymphocyte, and the lymphocyte, it's a small region in the in our core. So, in the biological meaning, we have a problem. If you will expose that we take in the different region, we will take the spatio-temporal equation. Why to use the alpha 1, alpha 2, alpha 3?
Okay, thanks a lot.
All right. Okay, yeah, so thank you once again, Adanani, for your talk.
Thank you.
And please, just in case, if you are not presenting, I will kindly request that you mute yourself. Okay, so there are some feedbacks that we are getting here. So if you are not talking or presenting, please kindly mute yourself. Thank you. All right, so the next presentation is by Mohammed Bujkara. So Mohammed, if you are online, please kindly proceed with your presentation. Okay, so Mohammed, are you online? Okay. Good. Okay, so I guess Mohammed is not online. So Hiham Sati.
Bonjour, moi je suis disponible.
Excuse me?
Bonjour, Mohamed Baji.
I can't hear you clearly. But then if you are Mohammed Bushkara, then please, yeah, you can share your screen and proceed with your presentation. What about Hicham Sati?
Yes, I'm here.
Yes, please. Please, you can start your presentation.
So I am going to present the poster.
Yes, correct.
Okay. Can you see my screen?
Yes, we can, but it's very small. So if you can, zoom in a little bit, that'll be good for us.
No.
Well, I guess that's the best it can. So, well, maybe if you're explaining, we can follow you. Okay. Mm-hmm.
Okay. So hello everyone. So the project I am going to present is the development of the neutron diffusion code using the model expansion method to simulate 3D reactors in Cartesian geometry. So to begin, I will start with a general introduction. The aim of this work is to present a deterministic calculation code developed by Photon 19 language designated for the neutron diffusion simulation in nuclear reactors. The code's name is Alpha Node. It solves the 3D steady state of the multi-group neutron diffusion equation in Cartesian geometry. The main method integrated into OpenNode is the nodal expansion method. It discretizes the space into a coarse spatial mesh, the nodes as large as a fuel assembly size. The best known equation that relates a flux and a current is the Fick's law. To develop for each node other equations relating nodal flux and partial currents to the faces of the nodes, a polynomial approximation of the flux is considered on the nodes by an expansion in polynomials up to order 4. The advantage of the nodal expansion method over other classical methods, such as the finite difference method, is that it doesn't require a very thin mesh to obtain the computational accuracy, thus a reduction in computational cost. The nodal expansion method allows the decreasing the number of unknowns by increasing the number of equations. For this purpose, two other approximations have been added for each direction. The first is the weighted residual method to obtain two other balance equations, and the second one is the quadratic transverse leakage approximation. The code allows to calculate the effective multiplication factor, the neutron flux, the radial, as well as the actual power distribution in the nodes. Besides, a graphical user interface was developed by Python to simply create the input file to run the source code, to plot 2D figures, and to design 3D geometries using Blender. Finally, to test the code, the comparison of the results calculated for excuse me. Okay. To test the code, the comparison of the results calculated for AA benchmark with those obtained by codes that use the finite difference method as a computational method was performed. So let us see the theory of the nodal expansion method. To establish the balance equation, we consider a Cartesian system of coordinates x, y, and z. The basic equation is the steady-state Newton multigroup Newton balance equation. If we integrate of the node both sides of the equations, we obtain the discretized form of the diffusion equation. At present, it's not easy to express directly and precisely the three-dimensional distribution. For this, we integrate the balance equation along y and z. It is the transverse integration, and we obtain a balance equation with a single variable, and this is the same for y and z. The unknowns of the nodal expansion method theory are the average fluxes per zone and the average partial currents at the face of the zones. The reason why the modern nodal method can obtain a solution with high accuracy is that the flux distribution in the node is expressed by a polynomial as is expressed as the equation 3. The discussion so far doesn't incorporate any essential approximation other than the diffusion approximation. So many approximations are considered here. In the one hand, the weighted residual method and P1 approximation, and the other hand, the quadratic transverse leakage approximation. The first one, I mean the weighted residual method approximation, allows us to give two more additional equations. Are the first and second order moment balance equation, as well as to relate the partial current leaving the faces of the nodes by net current. Then we can express the partial current. I mean, we can express. Sorry.
Sorry to interrupt, Sati, but Jafar, please, can you kindly mute yourself? Okay, please. All right, Sati, please, you can proceed.
So I will repeat. So many approximations are considered here. The first one is the weighted residual method, and the second one is the quadratic transverse leakage approximation. The first one allows us to give two more additional equations, are the first and second order moment balance equation, as well as to relate the partial currents leaving the faces of the nodes by net current. The second one is to calculate the transverse leakage terms by approximating the distribution in the node of interest by a quadratic formula using the average value of the transverse leakage of the node of interest and its two neighboring nodes. So let's us to see the results. In this part, I will present the open node calculation code that I have developed. The most important features of open node code are the source code of calculation is written in Fortran 19. The input is simple and flexible using a graphical interface developed with the Python language and softwares like PyQt Designer and Blender. It solves the steady-state core problems with the Cartesian geometry. It also performs direct and it performs the forward and adjoint and the forward adjoint and the fixed source problems. It solves the multi-group of Newton energy. It calculates the K-effective, the flux radial, as well as the axial power. It plots the radial and axial geometries in 2D and 3D. So the available node kernel is nodal expansion method. The idea of OpenNode is a graphical user interface display of several windows, allowing the user to perform interactive tasks. The user uses buttons which are located on the interface to activate certain functionality. For example, to enter the necessary input parameters, to compile the Fortran source code, to run it, display the output files, plot figures, draw geometries in 2D and 3D problems. The benchmark or the reference problem to validate our calculation is the AAAA. I mean the International Agency of Nuclear Energy. It is a benchmark reactor, is a two-group problem consisting of 177 fuel assemblies, including 9 rodded fuel assemblies, and a zone of water reflector with a vacuum external boundary. The width of each square assembly is 20 centimeters. So they are the 2D and 3D radial visualization of this benchmark geometry generated by OpenNode respectively. This is the 2 dimension, and this is the 3D dimension. The 3 dimensions, which the color in each of the assemblies indicates the material number. This table details the two-group cross-section data for all materials that describe the assemblies, and this table represents the result of the effective multiplication factor obtained by our code for different polynomial orders, as well as the node size, and are compared with other reference code. So we have used 3 different node size: the coarse mesh 20 centimeter, the thin mesh 10, and the very thin mesh 5 times 5, as well as the 2 differential polynomial orders, the second and the fourth order. And you can see that the very thin mesh structure provides the same reference value of chi-effective in only 2.7 seconds of computational time, whereas the reference value was obtained with 147,968 nodes in 4,080 seconds. So you can say that a good agreement between our code and the reference was achieved. The calculation method to cross mesh is core distribution of the Newton power and chi-effective value given by OpenNode code. These tables are compared to those obtained by the finite difference method. According to this table, the highest error related to the power distribution in the core is 0.43, whereas the lowest value is 0. And this is also approved this result. Traces the thermal and fast energy group. So to conclude, the OpenNode nuclear reactor code has been developed to solve the multi-group steady-state Newton diffusion equation in multi-dimensions. OpenNode uses the second and fourth order nodal expansion method to expand the flux, and the second order to expand the transverse leakage. A graphical user interface application has been developed to make the code easier to use for the user. To test the computational accuracy in OpenNode, the AA2D benchmark was applied as a test problem. The result of the nodal expansion method used in OpenNode showed the reasonable accuracy obtained compared to the finite difference method used in the venture reference code, as well as other references code based on nodal expansion method and the analytical nodal method. And finally, a good agreement between OpenNode and the reference was achieved when the mesh become thin, and thus the errors related to power and effective become very close to the reference values, except that the nodal method doesn't require extensive discretization like the classical methods such as the finite difference method to get close to the exact values. And thank you for attention.
So yeah, thank you, Sati, for your presentation. So any questions? Okay, so Fuseni, you have your hands up. Please unmute yourself and then ask your question.
Thank you for giving me the opportunity. I want to know where the concentration gradient is and then the equilibrium of the diffusion. Just the concentration gradient and then the equilibrium of diffusion. Hello? Hello?
Hello, sorry, I didn't listen.
Hello?
Can you repeat your question?
Yes. The concentration gradient and then the equilibrium of diffusion. Can you hear me?
Yeah, we can hear you, Fuseni. So
Yes.
I presume Sati too can hear you.
Okay. The concentration gradient and then the equilibrium of diffusion. That's what I want to know.
Sati, can you please hear Fuseni's question? Well, unfortunately, we lost Sati. So I guess then we move to the next. Okay, yeah, so he just joined. Hello, Sati. Sati, can you hear us?
Sorry, I lost my connection.
Okay. Yeah, Fuseni, please ask your question once more, then we continue.
I want to know the concentration gradient and then the equilibrium of diffusion. The equilibrium and then the concentration gradient.
The concentration gradient.
Yes.
If you mean the loss fit, I didn't understand the question clearly.
You are talking about diffusion.
Yes,
diffusion.
reaction.
Yes, and in diffusion, we have a concentration and it diffuses to where there is lower concentration. And there is a gradient that we have to take into consideration.
Yes, the gradient, yes.
Yes, please.
The gradient is an operator, sorry.
Okay, so I guess because of time, we will move on. So Fusaini, that's why there's going to be a networking section. So you can exchange, emails, and then maybe if you have further questions or you need more clarifications, you can, ask Sati. Okay, so because of time, I will proceed with the last presentation before the break. So Mohammed Bati, if you are ready, you can share your screen and then give your presentation.
Hello.
Yes, we can hear you, Bati.
Bonjour. Bonjour. Voilà, donc on va présenter.
Bati, if you can please speak English, we really appreciate it. Okay.
Est-ce qu'on peut parler français? Car moi, je suis parlé français mieux que l'anglais. Hello. Donc, on va présenter an efficient reconstruction of boundary data with the meshless method application to inverse Stepan problem one dimensional. Donc, pour le plan, donc on a pour le plan, on a introduction, formulation mathematics, and method fundamental solution, application the method the solution fundamental, and résultat numérique, and conclusion. Donc, pour introduction, donc nous étudions une application de la méthode des solutions fondamentales, application pour problème de Stepan inverse parabolique one dimensional, où les frontières, les limites et les conditions initiales doivent être déterminées. Le problème de Stepan possède une interface mobile donnée. Donc, la méthode fondamentale des solutions est une méthode sans maillage, nicheless méthode par rapport à d'autres méthodes. Les éléments finis et les différences finies. Donc, nous nous concentrons sur le problème de Stepan inverse pour modéliser le problème de Stéphane inverse permet de modéliser beaucoup de monde réel parmi l'ingénierie, par exemple la fonte de la glace, la solidification des métaux. Donc, pour la formulation mathématique du problème, le problème de Stéphane Derek est unidimensionnel. Donc, nous souhaitons de déterminer la frontière libre, notée RS, et la température UX de T, la température de domaine, la condition U représente la condition de la chaleur, la condition de la chaleur, donc le domaine c'est T 0S de T et 0T, T c'est le temps, sera donné. Nous avons une frontière X, X égale à 0, notée RU. On note l'union des frontières R égale à RS plus RU. Et la fermeture du domaine, c'est T bar. Donc, formulation mathématique. Voilà, on a l'équation de la chaleur, les conditions initiales, l'équation de la chaleur, la condition initiale, et aussi les conditions de bord, les conditions du type Dirichlet, et ici du type Newton. Voilà. C'est ça, c'est la formulation mathématique du problème de Stéphane. Ça, c'est la représentation géométrique. Voilà, ça c'est le domaine, c'est T. Ça, c'est la frontière mobile. Ça, c'est les frontières fixes. Ça, c'est les conditions initiales. Ça, c'est la condition finale. C'est T grand. C'est grand T. On peut aussi remplacer les conditions des frontières données par des frontières plus générales pour les frontières de Dirichlet et de Newton. Si c'est des frontières satisfait les conditions de comptabilité. Donc, pour le problème inverse de Stéphane qui sera étudié, nécessite de trouver la température, satisfait les équations, l'équation de la chaleur et les conditions initiales et les conditions de frontière, et les frontières mobiles SDT sera connu. Donc, le problème de Stéphane, d'après la littérature, possède une solution unique, car reste solution unique, mais reste un problème mal posé, car il ne correspond, il ne vérifie pas les conditions de Adam. Car si on a les petites perturbations, dans des solutions, des solutions n'est pas dans des problèmes pour des solutions à cause de la stabilité. Donc, pour régler ça, on utilise la méthode des solutions. On utilise la méthode, la régularisation de Chekhov. Donc, pour la méthode de fundamental solution, donc ça, c'est on a F, la solution fondamentale de l'équation de la chaleur, c'est F, tel que A, c'est la fonction Heisenberg. La solution fondamentale satisfait l'équation 1,10. Donc, et après, on va construire une approximation par la méthode fondamentale solution. s'accumule à l'infini. Et après, nous cherchons une solution entrant quand la série infinie et à la somme finie. Donc ça, c'est ça la solution par la méthode de solution fondamentale. Donc après, on va essayer de déterminer CMPI. Les constantes CMPI. Donc ici, on a représentation, on a le domaine. Donc on a le domaine one-dimensionnel, les frontières fixes x à 0 et les frontières mobiles donnés par S de t, x égale à S de t, et les sources placées moins h et h plus s. Les points sources sont placés au CA suivant y1 de taux m et y2 de taux m. Et aussi, on place le même nombre de points sources par le nombre de points de colocation sur les surfaces latérales. Voilà, c'est ça le domaine. C'est ça le domaine de la présentation du problème de Stéphane. Donc, la méthode de solution fondamentale obtient le système d'équations suivant. Ce système peut représenter en général par un système linéaire AC égale à F, tel que C désigne le vecteur de constante inconnue qui doit être déterminé après. F et le vecteur représentent les valeurs initiales et limites au point de A de colocation de source. Donc, on va essayer de trouver C. Donc, la résolution de ce système conduit ce système est mal conditionné. Donc, pour régler ça, on utilise la régularisation de Tchekhov. Donc, la régularisation de Tchekhov résout ce système. Donc, on va transformer AC égale à F par ce système-là. Ça, c'est bien régularisé. C'est que A là, le paramètre de régularisation. Nous notons que la résolution du système d'équation donne une approximation de vecteur C. Donc, si on a le vecteur C, donc on peut trouver la solution approchée, UM tel que C est connu. Donc, exemple d'application, on a ici en cours une exemple. La solution exacte est donnée par la solution exacte est UX de t exponentielle t moins x moins 1. Les frontières S de t égale à t et les conditions ou limites de l'intervalle sont données par, on a deux conditions aux limites. Ça c'est pour Dirichlet, ça c'est pour nous. Nous souhaitons récupérer les conditions aux limites de Dirichlet et de nous sur la frontière fixe. Ça c'est pour, on sait la condition initiale, on a la solution exacte, on peut déterminer ça par la solution exacte et aussi par la méthode fondamentale des solutions. Voilà, ça c'est la géométrie de domaine. On a S de T c'est une droite, ça c'est le domaine T. Ça, c'est pour le domaine en général. Ça, c'est pour cet exemple. On a le domaine, c'est suivant. Ici, c'est les points sources. Et ici, existent les points de colocation. Voilà le résultat. Ça, en bleu, on a la solution exacte. Et en étoile, on a la solution approchée. D'accord? Donc, on a quatre quatre, quatre figures. La première figure, on n'a pas une perturbation. La deuxième, on a la perturbation, c'est 0,01. Deuxième, c'est 0,03. Et la quatrième, 0,05. Si on augmente le nombre de perturbations, on voit qu'il y a l'erreur augmente l'erreur augmente avec la solution, l'erreur augmente. Ça c'est pour les conditions de déréglage. Ça, c'est pour les conditions de NumA. Ici, on augmente, on trouve la perturbation augmente plus que la condition de déréglage. Donc, ça, c'est sujet, ou bien sujet ouvert pour la recherche, pour la condition de NumA. Conclusion, nous avons observé que notre méthode reconstruit des données de déréglées. La reconstruction des données de NumA pose encore quelques problèmes. Donc, ça, c'est un sujet ouvert. De moins, dans certains cas, il nécessite une attention particulière. Nous examinons cette question dans les travaux futurs. De plus, nous montrons l'efficacité de cette méthode. On peut montreront l'efficacité de cette méthode pour les problèmes inverses à des dimensions. Moi, je suis travailler pour un domaine inverse à une seule dimension. On peut faire des dimensions. Merci. Thank you.
Thank you, Bati, for your talk. So any questions for Bati? Any questions for Bati Mohammed? Okay, so if there are no questions, then we now have a 30-minute break. Okay, so we resume in the next 26 minutes. Okay, and basically this is also the time for networking. So this is also networking time. So please, if you want to use the bathroom, restroom, or if you want to stay for the networking, please do so. Immediately after the break, we'll have the second plenary talk by Dr. Chris Bath from the University of Bath. Okay, so let's have a break and networking session, and then we resume in the next 26 minutes for our next plenary talk. Thank you.
Hello, Chris.
Hello, Stephen. Nice to see you.
Nice to see you too. How was your holidays?
Oh, it was lovely. We spent 2 weeks in Yorkshire, walking in the hills.
Okay, that's nice. That's nice.
Yeah, our dog came along and everything, so that was really nice.
Yeah. That's nice.
And how are
Yeah,
you?
so I'm also fine. I'm doing well.
Good.
Doing well.
It was so nice to see you in Bonn.
Yeah, also so nice to see you, Vaughn. I'm hoping to meet again with Franca.
Oh, yes.
Maybe next week. I'm planning on meeting her next week in Benin.
In Benin. Well, you will meet my son then.
Yeah. Okay. Jeremy.
Yes, so he'll be there.
Yeah.
Of course, you've met him already, but he'll be there with Franca in Benin.
Okay.
Oh, that's wonderful.
Oh, yeah, that's nice.
Oh, that's wonderful.
Yeah.
Yes, he's getting ready to go. And
Okay.
he's looking forward to it. Yeah.
Yeah, that's nice.
Oh, that's nice to know that there'll be someone else there that he'll know.
Yeah.
Oh, Franca's brilliant, isn't she? The way she gets all these things done.
Yeah.
I am most impressed with Franca.
Yeah, she's doing a lot. She's really done a lot, I think.
So she's going off to Caltech fairly soon, and my son will join her.
Yeah, she told me about it as well.
Yeah. So how's the workshop going?
Yeah, it's been nice so far. We've had a lot of talks.
Good.
Yesterday we had about 7 talks.
Uh-huh.
And then today, so far we've had about 5 talks today.
Good.
So it's going well so far.
And what's the weather like in Ghana at the moment?
Oh, it's sunny. Sometimes there are some showers, but largely it's just sunny. And yeah, and a bit cloudy with some little precipitations here and there. But largely sunny. The temperatures are around 26,
Okay.
26, 27, 28, 30. Then in the evenings or in the nights, it gets to maybe about 23.
I see. Yeah. Oh, that's not as hot as I thought it would be.
No, not too hot. No.
Yeah.
I was just telling some colleagues that it was warmer in Nice where I was last month. For July, in the whole of July I was in Nice in France.
Yes.
At NumA, and I told them it's warmer there than in Ghana.
Well, when I was in Yorkshire a week or so ago, we got to 31.
Oh wow!
But in the UK earlier on this year, we got to 41, and I ended up on telly because they wanted someone who knew about climate change to talk about what was going on. So I got interviewed about that.
Oh, that's nice.
Because I probably told you one of the projects I'm involved with is working with people in Nigeria.
Yeah, you told me. You told me about this. You told me about this. You told me about this.
That's my student Tozin.
Yeah,
from Nigeria. He's a good guy.
Okay. And how's it going?
So he's got till the end of this year for his PhD. Okay. We'll try and get him some extra funding to stay on for a few months extra. And he is going also to the Heidelberg Laureate Forum next month.
Okay.
To represent Nigeria, which that would be very, very good. So yeah, I'm sure he has a great career ahead of him.
Oh, that's good. That's good.
So I've had a number of students from Africa, so Tosin being one, but I've had others from Nigeria and also from Botswana. So if you have any good students that like to spend a bit of time in the UK, we're most keen to see them. You still there? Ah, we lost you.
Yeah, I'm having a bit of an issue in my office with the internet today.
Okay.
Yeah, so I'll actually be traveling to Kemenet next month for the Kemenet Symposium. And when I saw your talk, I realized something similar. I'll be making a presentation on mesh grading.
Ah, very good. Yeah,
clarity.
excellent. Well, then we can talk a bit more about that then.
Yeah, so I'll be making a presentation on mesh grading, but using discontinuous Galeckin methods?
Well, I use DG as well. I have a student just about to submit his PhD on DG and mesh methods.
Okay.
In fact, I spent all of this morning with him trying to sort of
Okay. Okay, that's nice.
Yeah,
so I'll be making a presentation. And I'll be meeting with Thomas Appel. I'm sure you know him.
Yeah.
He
Oh,
does
yeah.
a lot of research on mesh grading as well.
Yeah. Well, I ran a workshop on moving meshes quite recently in Edinburgh, which was great fun.
Oh, okay. Oh, okay.
Well, in fact, I'm writing the report on that, which contains a kind of list of kind of things that we discussed. I might even send that to you.
Oh, okay. Okay, that's nice.
Yeah,
That's nice.
I mean, I've been working mesh stuff for some time now. I started working when I had a sabbatical in Canada in the early 1990s, 1992.
Oh, okay.
Come people.
Yeah. So when I read the title, I was like, oh, okay, that's interesting.
Well, that's
I'll be making a presentation on discontinuous Galeckin methods for some singularities that are also occurring in elliptic problems.
well. That
So
sounds
basically,
good.
basically it's just change in boundary conditions that brings singularities, as well as when you have a kink in the center of the domain as well. How to do the mesh grading techniques for this.
So when you say singularities and elliptic problems, are these linear or non-linear problems?
Like, no, I mean, all the problems I'm presenting are linear.
Linear, okay.
Linear, yeah.
I mean, I've done a lot of work in both linear and non-linear elliptic problems.
Okay.
With singularities, and developing mesh methods for both. I mean, they're subtly different.
Okay.
Oh, then we're going to have lots to talk to each other about. That's great. So are the participants at this workshop mostly from Ghana, or are they from all over?
Hi, Chris. This is Osei. I'm the
Hello.
coordinator. Yeah. So
Hello,
I guess I guess Stephen has some internet connectivity issues. Yeah. So
yeah.
can you hear me now?
I can hear you very well, Osei.
Okay, good. Yeah. So we have participants all over Africa. You know, from Ghana, Nigeria, Morocco, Algeria, and even some from Pakistan. So it's all over the
Oh wow.
Mm-hmm.
I've sadly not visited Ghana yet. I've been to bits of Africa, but not to Ghana. So hopefully one day.
Yeah, sure. Yeah, I mean, you should visit. You'll love it there.
Funny enough, my son is going to the same workshop as Stephen in Benin next week.
Oh, okay.
So he's a postdoc now, so that's
okay.
all right. Working. Do you know Franka Hoffman?
Okay. Mm-hmm.
Oh, here comes Stephen again.
Okay.
Yes, internet's annoying when it's like this, isn't
it? Yeah, absolutely. Mm-hmm.
What can we do, eh? It looks like you're in San Francisco.
Yeah, that's my background.
Yeah, I did a sabbatical for 6 months at the MSRI in Berkeley, and I could see the Golden Gate from my window.
Okay, yeah. Well, actually, I was there in February. Yeah.
Oh, how splendid! It's
exactly.
It's nice out there. Yeah.
Mm-hmm.
What sort of stuff do you do, I say?
Okay, yeah. So I'm into data science. So I develop models, stochastic differential equation, so model, time series data.
Excellent stuff. Oh, right.
Yeah.
Very hot topic nowadays.
Yeah, it is.
So you're doing what? RNNs, LTSNs, that sort of stuff, is it all?
Yeah, correct. Yeah, and I also do some machine learning as well, some machine learning modeling as well. So
we've just started up a big kind of thing in machine learning in Bath, which I'm directing. So maybe we can encourage you to visit at some point.
Okay, yeah, that works.
Yeah,
sure.
So can we just do a check? I just want to check I can share screen and share my presentation.
Yeah, please go ahead.
So, because I had some slight issues with this earlier. Now.
Okay.
Can you see something?
Yes, I can see your screen. Yes.
Excellent. Well, I'll stop sharing for the moment,
okay.
And then we can be ready. We're ready. Well, that works at least.
Okay.
All
right. Hi everyone. Welcome back from the 30 minutes break. So we now move on to the next item. So the next item is the plenary talk by Professor Chris Batt. Professor Chris Batt is a British mathematician, and he's especially known for his contribution to nonlinear differential equations and the applications in the industry. He's currently a professor of applied mathematics at the University of Bath and a professor of geometry at Gresham College. And today, Professor Chris Batt will be presenting on the talk Moving Meshes in Non-Convex Domain. So, Prof. Batt, we are honored to have you today.
Well, it's really great pleasure to be here. So let's share screen. Hopefully you can see all that fine. Well, thank you for the invitation. I'm really sorry not to be with you in person. I've heard lovely things about Ghana, and I do hope I can visit you at some point. Funnily enough, my son, who works in machine learning and mathematics of that, is going to be in Benin next week, so he won't be very far away. So if you see another bud floating around, that will be my son. So I'm going to talk today about moving meshes, which is a subject that I've been interested in for many years. And we're going to have a look at moving meshes when you're looking at differential equations in non-convex domains. And the key feature about these is that solutions of PDEs in non-convex domains typically have singularities, and that's why you need to have some sort of moving mesh. And this is a joint work between myself, Simone Appola, who did most of the work, who's a PhD student of mine just finishing, going off like everyone else to be a data scientist, and Tristan Pryor, who is a colleague of mine also at the University of Bath. Right, well, let's set the scene then. So the idea is that we want to solve a partial differential equation. And imagine that we want to solve this using some sort of method. Typically, that might be a finite element method, discontinuous Galerkin, for example. And if you have a finite element method, then you need to construct a mesh to do that. And I'll call the mesh Tor. And as the solution of the PDE evolves, or as we understand more about the errors that we're making when we solve the PDE with the finite element method, we generally want to update the mesh as part of the solution process. And there are typically two different ways of doing this. One is called mesh refinement. And in mesh refinement methods, you might take a mesh, which might be, say, triangles. And if the solution of your PDE has a high error, then you might want to divide that triangle into smaller triangles to reduce the error. And that's generally called H adaptive, H being the idea of the step size, the mesh size, and adaptive meaning you reduce it to reduce the error when solving the PDE. An alternative method, which is called R adaptivity or mesh relocation, is where you take a mesh with a fixed number of points, and rather than subdividing the triangles, you move points closer to each other where you think the solution may have a higher error, or move them further apart where the solution may have a lower error. And this is called R adaptivity or relocation adaptivity. And one of the key ways that differs from H adaptivity is that if you move points around, you typically keep the mesh, the number of points in the mesh fixed, and the connectivity in the mesh fixed. Now, if your PDE is a parabolic or hyperbolic PDE where you have some notion of time evolution, then typically the mesh will move as the solution evolves, and then that's why these methods are often called moving mesh methods. Okay. So this is the idea, and basically I'm going to talk in this talk about the way that you might move a mesh or relocate a mesh, and how that can be done very effectively, even if you're working with problems with singular solutions. Now, relocation technology is relatively new. It's not been around for as long as the kind of H adaptive mesh refinement, and the kind of big codes that are typically adaptive codes do adaptivity by H adaptivity. But there are many, many advantages that R adaptivity has over H adaptivity. One is that you can have very nicely graded meshes. I'll show you an example of this in a minute. So when you have if you have a triangle and you divide it into two, you get a jump in your mesh size where it goes from 1 to 2, which is quite a big jump. Whereas if you move the points, you can have much more graded meshes. So you can get nice regularity bounds from that. Another is that when you develop meshes, you always want to know what the quality of the mesh is. That's generally expressed in terms of skewness or small angles and something. And that's quite hard to control with an H adaptive method, but is actually very straightforward to control with an R adaptive method. Another advantage of these methods is that because you've got a constant mesh connectivity and constant mesh number, the topology of the mesh is unchanged. So when you're doing H adaptivity, you might have some sort of ordering of your mesh, but as you start to refine, so the ordering gets very complicated and you have to build quite complicated data structures to deal with that. If you just move mesh points around, then you don't need to do anything like that. You have constant data structures and life gets a lot simpler. And finally, if you're doing things in parallel, if you're keeping the same number of mesh points, then it's much easier to balance operations over the mesh. So there are many, many advantages that R adaptivity has over H adaptivity. Why isn't it used as much? Well, one reason is that it's somewhat harder to set up. It's very easy just to divide a triangle. It's harder to move mesh points around. And a second is that it's got a bit of a bad reputation for introducing tangling in a mesh where mesh points cross over each other. And that means that people are kind of reluctant to use it for that reason. But I'm going to describe a method which completely avoids that problem, which allows you to build meshes without any problems of tangling. So there we are. That's the motivation behind moving meshes. And that's what I'm going to be largely talking about today. So here's, to whet your appetite, an example of a moving mesh or an R-adaptive mesh for computing the solution of an elliptic differential equation within a T-shaped domain. So T-shaped domain is a non-convex domain. You have re-entrant corners, and at the re-entrant corner, you have a singularity of the solution. The solution gradient becomes infinite as you go towards the corner. That, if you're solving a problem like an electrical field problem, that will correspond to an infinitely high electric field. And so you need, in that circumstance, to have a mesh which is refined close to the corner. And here is one that we've generated using the technology, which I'm going to describe in some detail in this talk. And you can see that the mesh has really got quite a lot of very nice features. It's concentrated by the corners, which is where you need it to be concentrated. It's got nice regular triangles. There are no small angles in the triangles. And you've got lovely grading towards the corner. And so this is a mesh that one would be very happy to compute the solution on, typically using some sort of a discontinuous Galerkin method. DG methods are very appropriate for problems when you've got non-uniform meshes. So this is kind of the objective. And what I'm going to show in this talk is firstly how you can construct such a mesh, both in a most general case and then in the specific case of problems with re-entrant corners. And then I'll show you how you can prove that the mesh that you end up with has very nice global regularity properties, which can then lead to very accurate solutions of the underlying PDE. So that's our overall motivation. Just to say one thing, what I've shown here is a mesh for a two-dimensional problem on the plane. The methods I will describe can also work on curved manifolds. You can do meshes over the sphere and can work in 3 dimensions or even higher if you want. So there's no real limit to what you can do. Okay, so how does R adaptivity work? So the idea between R adaptivity is that you have a mesh, going back to our picture here, which has cells. Here are our cells here. And if something interesting is going on, for example, if there's a singularity, you want the cell to be small. In other words, you want the cell to have a small area. So the basic idea behind how these things work is that you have some function m, we call it a monitor function, which is large where you want the mesh to be refined. So if there's going to be a large solution error, m could be a monitor of the solution error. And you simply arrange so that the monitor function times the cell area is constant. And that means that if the monitor function is large, then the cell area must be small. And equivalently, if the monitor function is small, then the cell area is large. And that's the basic idea. It's called the equidistribution idea. This is a very old idea. It goes back to De Boer in the 1960s, if not before then. And in fact, the radon back in the 1915 essentially showed that almost any transformation can be expressed in terms of this kind of equidistribution idea. So when you're doing mesh relocation, one of the first things that you need to think about is what would be a suitable control of your cell area, what would be your monitor function that you want to use. Well, there's lots of different possibilities. One which has been around for quite a long time, but still has a lot of mileage, is to make M some measure of the a priori error of the solution. So that could be, for example, an error, a measure of the interpolation error of the solution. So if you interpolate a solution with piecewise constants, then the a priori error is proportional to the gradient. And if you approximate the solution with piecewise linears, then the interpolation is proportional to the curvature. So you might want monitor function to be the gradient, norm of the gradient to some power, or the norm of the curvature to some power. So if that's your monitor function, that would ensure that the function u is represented well in some sort of interpolation sense. Okay, so that's one method. Another method is to look at the underlying physics of the problem. So a lot of my own work is done in meteorology, and ask any meteorologist what they want to preserve and they'll tell you vorticity, always vorticity. So it's reasonable to have your mesh concentrated where the vorticity is large, so you'd make M the vorticity. Another method, which we'll talk a bit about later on, is you do a computation, you make some a posteriori or error estimate of the computation, which in finite element methods is relatively straightforward, and then that becomes your measure. And a final and really quite exciting new development is to combine all these sort of ideas with a modern machine learning, and you will train your method on a lot of examples, and the method learns an appropriate monitor function from those calculations. And Jason Walbrook at Imperial College has been pioneering ideas along those lines. So that's how you might choose your monitor function, and there's a whole sort of science associated with that. So let's show you then how this works. Here's an example on the right of a mesh which has been computed by taking a monitor function which is large in a ring centered at the origin. And this is a mesh that we computed once for solving a problem in laser physics. And you can see that the mesh is really quite nicely concentrated around the ring. And the way this whole process works is you take what we call a computational mesh in a computational domain, which is regular in every way, and you map that into the physical domain, and the map itself encodes the mesh within it. Now, if you do H-adaptive meshes, then you have to talk about cohomology and all sorts of fancy topological ideas to describe the mesh. In our adaptivity, it's much simpler. The mesh is simply the image in the physical domain of a regular mesh in the computational domain. So that's how the process works. And as I say, you make that image concentrate the points where the monitor function is large. So we think of this map then from the computational domain to the physical domain. We'll assume that this map is differentiable and has a Jacobian, which is defined in the normal way. There's our map. And then the cell area in the physical domain is the determinant of the Jacobian, or the modulus of the determinant of the Jacobian. The equidistribution requirement then becomes the very straightforward expression that the monitor function times the determinant of the Jacobian is a constant. So that's the equation that we're interested in solving to find the map from the computational to the physical domain. It's a fully nonlinear equation, so that m times det j is constant. And that's our equidistribution requirement. Anyone that's interested in measure theory will recognize this m here as playing the role of a measure in the physical domain. Okay, so that's how we're going to set up our mesh. So there's good news and bad news here. In one dimension, the equidistribution equation, m det j is constant being theta, defines the mesh essentially uniquely. And this was understood ages ago. De Boer knew about this. Codes like Colsys and so on use this requirement. That in 1D, that requirement, if I ask you to give me an interval of length 1, up to translation, there is only one interval of length 1. But in 2D or 3D, there is no such simple uniqueness. The condition number 1, the equidistribution condition, doesn't uniquely define anything. If I ask you to give me a set of area 1, then there's an uncountable number of sets of area 1. So we need to augment this condition on the mesh with some other condition which specifies it uniquely. And there's, well, you open up the textbooks on mesh adaptation and you'll find lots and lots of ideas on this. But an idea I came up with in 2006, together with my student Jeff Williams, who's now at Simon Fraser University, which others came up with at about similar sort of time, was as follows. If you open up the great textbooks in numerical analysis about how to discretize PDEs, they go on at length about the very great advantages of having a completely uniform mesh to discretize a PDE on. If you have a uniform mesh, you get nice cancellation properties, you don't have problems with small angles and all that sort of nonsense. So the simple idea is, well, if uniform meshes are so great, why don't we find a solution of the equidistribution equation which is close to uniform as possible? And how can one describe closeness? Well, an easy way to describe closeness is saying that it has to be as close as possible in L2. So Jeff and I thought, well, can we solve equation 1 by looking at the solutions of equation 1, which minimize the deviation of the mesh away from a uniform mesh? So that's a simple idea, but immediately we can see things that are going to happen in this. If we're trying to find a mesh which is close to uniform, the uniform mesh is untangled, and therefore we would expect the mesh we come up with also not to have tangling. Secondly, a uniform mesh is not skew, so we would expect the mesh that we get not to be skew. So those are two things you might immediately expect. Now we can make this completely rigorous, but immediately you can kind of see the virtues of this idea. But like everything in life, you come up with an idea and you find someone else has really thought about it before. And in this case, the person that had thought about it was Monge, who was scientific advisor to Napoleon during the Napoleonic Wars. What's the idea behind that? Well, it was Monge who was looking at the question of whether you could move Earth from one hole to another as easily as possible. And he came up with the idea, which we now call optimal transport, of the optimal way to move Earth from one hole to another. So this is Monge's kind of problem. And then it was realized in the 1920s that this problem related very strongly to problems in economics, where you might want to transport goods from one place to another. And it was developed by Kontarovich and became the Monge-Kontarovich problem. And in the 1991, Jean Grenier in Paris studied this problem in the context that I'm interested in it, where the difference is the L2 norm, proved a quite remarkable theorem. I'm really annoyed that he wasn't awarded the Field Medal for it at the time, because it's so amazing, this work. And he proved that if you want to solve the equation m times det j is theta, which is the equidistribution equation, then there is a unique function which minimizes that L2 norm. This is the thing that we want to do. So that tells me that I can construct a mesh. And then Grenier went on further. He actually showed a way of doing it. He said that what you end up with is a function which is the gradient of a convex, what I call potential function phi. So the map from the computational domain to the physical domain, which equidistributes the monitor function and also minimizes the deviation from uniformity, is the gradient of a convex function phi. And this is wonderful. It's pure magic. Why is it magic? Well, it tells me that a mesh exists. It tells me that I can compute it. And it tells me that I don't need to worry about complicated geometrical structures all I need to do is find this function phi, which is a scalar function. And then once I differentiate it, I've got my mesh. Phi is a scalar function. So if I want to mesh in 2D, I construct phi and take the two-dimensional Laplacian gradient. If I want it in 3D, I take the three-dimensional gradient. I can do 2D meshes and 3D meshes just as easily. You can also do this on manifolds. You've got to work a bit harder, but you can extend Brenier's results. Robert McCann extended Brenier's results to manifolds. As I say, I was annoyed that Brenier didn't get the Fields Medal. More recently, Figali, who was essentially extended Brenier's results, did get the Fields Medal. Richly deserved, but Brenier should have got it earlier. Okay, so let's talk a bit further. It's actually slightly easier, rather than using Brenier's result, where x is the gradient of potential, to let x be the original mesh plus the gradient of potential, which amounts to the equation I put underneath, which is a little bit better for domains with periodic boundary conditions and generalizes to manifolds such as the sphere. And you want to do the sphere if you're going to do meteorological work. Okay, so that's Brenier's result. That doesn't tell us how to find the mesh. Let's see how we do it. So if you take the function x as psi plus grad phi and differentiate it, then the Jacobian is the identity plus the Hessian, the second derivative of the potential. The governing equation then becomes the monitor function, which is a function of x, which is in turn a function of gradient of phi, times the determinant of yi plus the Hessian of phi equaling the constant. And that is the equation that we solve to find our mesh. And this is called the Monge-Ampère equation, named after Monge again. Ampère, the great French scientist in the 19th century. And if you write that down in 2D, then it becomes that fully nonlinear elliptic PDE, m times essentially the second derivatives of phi multiplied together is constant. So that's the equation that we have to solve to find phi. And once we found phi, we take its gradient and we get the mesh. Okay, just a little bit extra. This is fully nonlinear. Everything you look at in sight is nonlinear. And you augment this with boundary conditions, which basically are that's the boundary of the mesh of one dimension mapped to the other. Or if it's periodic, then you put in the periodicity. If you're solving on the sphere, you don't need boundary conditions because the sphere has no boundary. Okay, so that is the Monge-Ampère equation. And there's lots and lots of literature on that. There's vast amounts of literature in geometry journals about this equation. And there's a certain amount of literature in numerical analysis papers about how one solves this numerically. Now, I should say one thing that's really important. We're talking here about generating meshes to solve partial differential equations. I'm interested in solving the PDE accurately, but you don't need a brilliant mesh to solve a PDE accurately on, so we don't need to solve the Monge-Ampère equation particularly accurately. So pretty well any method which solves it to some degree will be fine, providing it's stable and it's fast. Okay, so we want to solve the equation in blue, but we don't need to solve it too well, and that's important because we don't want to spend a lot of time solving the mesh when actually what we really want to solve is the PDE itself. Okay, so that's the equation that we're going to solve. Let's talk about how we solve it. Well, the method that we used to solve it was derived by Tristan Pryor, my colleague in Bath. This was before he came to Bath. I think he was in Reading at the time, working with a PhD student called Lakis. And the idea behind solving this is rather like if you want to solve Navier-Stokes, you have a mixed finite element method, So you discretize velocity and pressure differently. And in this case, we introduce a new variable sigma to represent the Hessian of phi. And then you discretize sigma and phi on two different function spaces, V1 and V2. And you decompose the Monge-Ampere equation into an equation for solving for phi, knowing sigma, an equation for solving sigma, knowing phi. So in red, we have the mixed finite element representation of the two equations that we want to solve, and we have slightly different types of space. So typically we want higher order space for sigma than for phi. And here are the kind of different types of space that we might want to solve it on. So we basically discretize the Monge-Ampere equation using a mixed finite element method using these spaces. And I should say that it was Pryor that came up with this idea, and then it was implemented numerically by Andrew McRae from Oxford later on. So this is how we solve it numerically. We write it in weak form, and there's the mixed finite element discretization. Various ways of solving this. You can either solve this in a relaxation method. Awanu came up with a very, very effective one. PMA is one I came up with earlier, which was anything like as good. Or alternatively, we can use some sort of Newton method to solve 2 and 3, and this is what McRae at Oxford developed in order to be able to solve the Monge-Ampere equation. As I say, you want to solve it quickly, so it doesn't really matter which method you use, providing they're reasonably fast. Let's have a look at some examples. Here's a couple of examples that we're going to kind of think about. The first, well, they're basically two cases. There's our monitor function up there. And if you choose certain variables in the monitor function, it concentrates around a ring. And if you choose other variables in it, it concentrates around a bell. We use these as monitor functions because they problems I'm particularly interested in problems in solving Schrödinger type equations where you might get singularities forming around rings or around single points corresponding to various types of focusing problem in lasers. So those are our two cases. And here is the solution if you use the relaxation method, where you essentially take the mixed finite element method and iterate it in a fixed point way for a number of times. And this is essentially an expanded version of a picture we saw earlier. And I want to kind of draw out various features on this. You can see that within the ring, the mesh could not be more uniform. Outside the ring, the mesh has distorted itself to meet the ring, but it still has very nice gradient properties. And around the ring, the mesh beautifully aligns itself in order to kind of align the elements along the ring as you go around. So that really does look a very nice mesh. It has lots of nice properties associated with it. And this is how the convergence works if you do an iteration. And what you do is you monitor the residual of your finite element calculation, and it goes down nicely. Here's the mesh that you get if you have a singularity in the middle. Again, I want to draw your attention to the fact that the mesh here in the center is again extremely irregular. It's basically squares. It could not be more regular. You get outside this what I call a cloverleaf pattern, and you can prove exactly why you get this as the mesh adjusts itself to fit the boundary of the domain. And we do get some small angles, but they are not that small, and essentially you can constrain the level of small angle that you get. So that's a perfectly good mesh. You could easily use that to compute singular solutions of PDE. And in fact, we do that. So I've done a lot of work on blow up in the non-linear Schrödinger equation, where the solution might get to 10 to the 100 in size. At the same time, the mesh has a compression of a factor of 10 to the 10, and it follows it very nicely throughout that. Again, the relaxation method to do that works very nicely. And just to kind of say how the Newton method works, this is the technique that Andrew McRae came up with. So there's our residual that we have for the mixed finite element method. And typically we use a quasi-Newton method, which suppresses some of the dependency of M on the function, and incorporates a nonlinear solver. And that works pretty well, actually. It's pretty robust. It's relatively easy to implement. And in the green, this is the ring problem that we looked at earlier. You can see the convergence of the quasi-Newton method is significantly faster than the relaxation method. So in a sense, the method of choice then for solving, for finding meshes on the sort of domains that we might be interested in is to use a quasi-Newton method, mixed finite element discretization. And that works very well for the plane, it works very well for 3D, and we've also got it to work pretty effectively on manifolds such as the sphere. Okay, so the title of this talk is Moving Meshes for Non-Convex Domains, and I've spoken a lot about moving meshes. What about non-convex domains? So let's have a look at this. And I was told when I started thinking about these that this could not be done. And the reason people told me it could not be done is you can't solve the Monge-Ampère equation in a convex domain because you get singularities and so on. And it was only after trying it that we realized that didn't matter. And I'll try and explain why as we go through. So we're going to have a look at what is actually quite a classical problem, well studied in the literature, of how do we solve Poisson's equation, minus Laplacian u is f. Well, I'll assume f is regular, and that u inherits whatever regularity you need, with Dirichlet conditions and Neumann conditions are on the boundary. And we'll have a convex domain. The one I've drawn is what we call the L-shaped domain, but you can have a number of different types of non-convex domain. With a re-entrant corner, I'll label AI for whatever the corner might be. So that's what we're going to use as our test problem. And the key thing is that U, the solution, has a singularity at the interior corners. And the way you can measure this singularity is that if R is the distance from the corner, so here's my corner, R would be some distance away from that corner, see up to there, then the solution looks like R to the alpha f of theta, where theta is just angle, where f is a fairly slowly varying regular function of theta, but R, the alpha value depends on the corner. So if you have a L-shaped domain, the interior angle is 3 pi over 2, so alpha is 2/3. So u theta is r to the 2/3 f of theta, so its derivative is r to the minus 1/3, and that goes to infinity as r goes to 0. And there's our singularity. So that's typically what things look like at corners. And if alpha was, say, 2 pi, which is even worse, then you would look like r to the half. So this problem's been studied forever. Babushka and Guo essentially showed an optimal Sobolev error estimate. where U is in some weighted solvable off space indicated as above. So the challenge that we addressed ourselves, and this was essentially my student Simone's part of his PhD, was to see whether we could adapt the kind of Monge-Ampere optimal transport moving mesh method to work in this sort of context, and then compare the sort of errors that you might get with an H adaptive method. And we're going to discretize this problem using a discontinuous Galerkin method. I won't go into any details about the method. Suffice to say, it's a classical finite element method where we're going to discretize on a triangulated mesh. We can see here the sort of mesh that we might be using. This is a sort of sneak preview, is actually the sort of mesh that is constructed using the Monge-Ampere type technology, where we have corner points and all sorts of nonsense like that. So that's our discretization. I won't go into a great deal of detail. We use piecewise linear discontinuous Galerkin method for the discretization. One of the nice things about this approach is that there are good a posteriori ori error estimates. And what I've shown in the red is one of these sort of typical a posteriori ori error estimates, which allows you to make an estimate of how big the L2 error is or L infinity error is in any of the cells. And then an H adaptive method reduces the cell size if that estimate is large. And I've shown underneath a typical mesh that you get when you do that, which I personally don't particularly like. It's quite irregular in a way. Yes, it's refined close to the corner, but there's no sort of niceness. It's not particularly symmetric. There's no good grading in there. And so whilst that would give you low errors, it's hard to construct, and actually the errors are going to be increased by the lack of regularity. So that's the classical adaptive method for this problem. Let's have a look at how we might adapt a mesh using more the kind of ideas that we've put earlier. So the idea here is we've shown that a good way to construct a mesh is to solve a Monge-Ampere equation. And in the context of the problem we're interested in, the main area we want to construct an adaptive mesh is close to the corner. So we may not have to solve the Monge-Ampere equation everywhere. We may just need to solve it locally close to the corner. And so our idea was, well, let's find a local solution, the Monge-Ampere equation close to the corner, use that to redistribute the mesh, and maybe use a monitor function based on interpolation error estimates. So that's the idea. The kind of thinking then further on is that the key thing about singularity of the solution is that it's a singularity in R, the distance from the corner. It's very slowly varying in theta. So we consider a monitor function which is only a function of R and has no theta variation. And the Monge-Ampere equation, if you do that, becomes a thing in black. M times R dr d theta is S ds d theta. That reduces down to the very simple equation in red. M R dr is S ds. And that is the Monge-Ampere equation if you ignore theta dependence. Well, that's a nice, easy equation to solve. You don't even need to use a numerical method for that. You can integrate that up very quickly if you know what M is. And noting that the solution of the underlying PDE looks like R to the alpha, we postulated that a monitor function which might work might be R to the minus 2 gamma. Don't know what gamma is yet. Let's see what we can do. if you substitute that into the Monge-Ampere equation, you get the equation in blue. If you integrate up, you get the equation in black. And then the local mesh size, dr by ds, just works out as being r to the gamma. So that is what gamma is. It's essentially how the local mesh H scales as we go away from the corner. We can actually work out what gamma should be in various cases. If you look at interpolation error, with u looking like r to the alpha f of theta, then the infinity, L infinity interpolation error over a mesh of a cell of size h turns out to be h squared times the second derivative of u, which is h squared r to the alpha minus 2. That tells me that h looks like 1 minus alpha over 2, which tells me that gamma in the solution of the Monge-Ampere equation is optimized by taking it to be 1 minus alpha over 2. So for an L-shaped domain, alpha is 2/3. So gamma is also 2/3. And in the crack, alpha is a half, so gamma is 3/4. So this is brilliant. This tells me what the optimal value of gamma is, and then that gamma can be substituted into the monitor function m in order to solve the Monge-Ampere equation to find the mesh. You can do the same in L2. There's various technicalities in the way things work, but the bottom line is that the gamma for L2 is 4/9 for the L-shaped domain and is a half for the crack. Okay, so how do we solve this? What you do is you take that value for gamma, you need to regularize the monitor function a bit so that it tends to uniform mesh away from the corner. You can then solve the Monge-Ampere equation analytically and can complete the mesh by matching from the local to the global solution with that value monitor function and that value for gamma. And that procedure, it's almost more complicated to write down than it is to do, because you've done most of the work by doing the analytical calculations. And these are the sort of meshes you get. So here is an L-shaped domain where I've taken gamma here to be this number 2/3. And you can see the mesh that you get there. This is by solving the Monge-Ampere equation. I'd just like to compare that mesh with the one that you get from H refinement, which is that, which is all over the place. And this one is beautifully regular, lovely grading, matches the boundaries, got all the symmetries you could want. Here's the same mesh for a crack domain, where you actually have alpha as 2 pi. It's really a very hard problem, and yet the method naturally goes in and produces the mesh, so that's absolutely fine. So those are the meshes that we get. We'll have a quick look at the errors of those in a minute. But I just want to say something else. One of the key things about meshes is that you want to understand properties of their regularity. And two measures that are important. One is the scaling of the mesh elements, and the other is the skewness. And if you have a map with eigenvalues λ1, λ2 as the map from one domain to the other, the scaling becomes the product of the eigenvalues, and the skewness measure is essentially a ratio of the eigenvalues. That's this number Q. For a completely uniform mesh, the scaling is whatever you have, it's constant, and Q is identical to 1. For an H-adaptive mesh, who knows what these numbers are? You know, you can't do the calculations, but with the sort of meshes that we're talking about, the Monge-Ampere optimally transported meshes, you can actually estimate these numbers absolutely exactly. And here's a calculation that Simone did. I was very happy with this calculation when he did it. he came up with the estimate QK at the bottom for the skewness, which shows that providing gamma is bounded away from 1, so 2/3, for example, that the skewness can be exactly estimated. It's bounded away. It's nice and finite. It doesn't increase as you go towards the corner, and it doesn't change as you change the number of degrees of freedom of the mesh. So it does a really nice job of globally controlling what's going on. So let's look at some results. So here are some results where we take the L-shaped domain and we compute the solution. In this case, there is an analytical solution you can get by conformal mapping. So you know what the actual true solution is, and then you can see how the solution depends on the mesh. And in green, we have the L-infinity error as a function of gamma. In the red, the L2 error as a function of gamma. And as you vary gamma, you get a very sharp dip precisely at the optimal values that we've predicted of 2/3, and in this case, a 4/9. So that piece of the analysis is right. Here's the error, again, as a function of gamma, as a function of number of degrees of freedom. So the key thing here is to see that the black curve with gamma is 0. Gamma is 0 basically corresponds to a uniform mesh. The blue curve is the optimal mesh, and you get much faster rates of convergence with on the left L2 and on the right L-infinity with an adaptive mesh than you do for a uniform mesh, far greater rates of convergence. And also you do very much get the highest speed when the monitor function accurately reflects the error. And the bottom two pictures show how the skewness, and mu is another measure of mesh regularity called the shape regularity, vary with dimension, and you can see they're dead constant as predicted by the theory. Here's a demonstration of the fact that the error for the adaptive mesh, that's the red, is the mesh, OT mesh, goes like essentially the 1 over the dimension, which is the optimal rate. The unstructured uniform mesh goes like 2/3, which is much slower. And if you compare this with H refinement, which is the green, we pick up exactly the same rate of convergence, if not better, using this method. And it's much better than not using adaptivity. And here is a comparison of the cost. Somehow we've managed to obscure the scale. I apologize for that. But the top few curves are H refinement with various scaling laws. Bottom, we have the optimal transport Monge-Ampere refinement with various scaling laws. And the Monge-Ampere R refinement method is about 2 orders of magnitude faster than the H refinement method for producing comparable, if not better, results. Okay, so I was pretty well finished there. I just want to say that if you want to move a mesh result on the plane, then a good way of doing it is to solve Monge-Ampere type PDEs using a mixed finite element discretization, and quasi-Newton works very well. The great thing about this is you can prove regularity, and the methods work as well as H adaptive, but are actually much easier to implement. Where are we going at the moment? Well, the sort of work I'm interested in at the moment is adapting these methods to building in these kind of more machine learning ideas where we learn the right monitor function, and this is collaborative work with Imperial, and also getting them to work on more realistic problems, and particular sort of meteorological problems that I'm interested in, looking at solution on the sphere in when we've got a very large and nonlinear systems. And if anyone's interested, there are some references, and my student Simone's thesis I have here, just about to be submitted, which has a lot of this stuff in it as well. With that, I will finish, and thank you for your attention. There we go.
Awesome. Yeah, thank you, Chris, for your awesome presentation. So time for questions. So please, if any of you have questions, you can use the button there to raise your hands, and then we will call you, and then you ask your question. Any questions? Any questions for Chris? Okay, yeah. So I guess then there are no questions, Chris. So I think that is that's amazing talk, and I believe we all understood it clearly. So
Let's hope so.
yeah.
Anyway, I look forward to interacting with all of you in Ghana more in the future, and maybe come over and actually see you sometime.
Absolutely, sure. And thanks so much for your talk. We appreciate it.
Okay.
Okay, thank you, Chris. Yeah. So yeah. Okay, so then we move on to the next presentation, and for the next presentation, we have Fatima. Fatima, are you available?
Yes, I'm here.
Okay, all right, sure, please. So okay, so well, there are two Fatimas. Okay, so we have Fatima Zoria. Okay, I think Fatima.
Yes.
Yeah. Mm-hmm.
Hello.
Hello. You can hear me?
Hello.
Yes, Mr. Otere, we can.
Okay, hello, can you hear me? So, can you hear me?
Yes, we can hear you.
Okay, I think after from your program, after the plenary talk by the professor, we have on the list, next one is Ricardo. Yeah, I don't know if you skipped that name.
Oh, no. Ricardo presented yesterday. So
okay, then after Ricardo is Mohamed Bati. That's what I can see.
No. So well, because yesterday some of the people presenting were not available, so we've changed the schedule right now.
Okay, so we're not following what's the program in front of me.
No, we are not following that. We have a new schedule that we are following. So maybe let me share my screen so you can at least have an idea on how it's going. Yeah.
I can start.
No, wait, Fatima, please hold on. I think according to my schedule right now, okay, according to my schedule of hello.
Yeah, can you hear you? Yes.
Can you all hear me?
Yeah, I can hear you.
Okay, good. Yeah, so this is the schedule. So at the moment, Fatima Zura will be presenting, And then after Fatima Zora, then Ikechukwu Otede will present. Then Johnson will go next. Muhammad Shimi. Then the last person presenting today will be Fatima Shoshi. I'm sorry if I didn't pronounce your name correctly. So this is how the schedule is going to, be.
Okay.
Yeah.
Okay.
You're welcome.
Okay, good. So with that said, okay, Fatima Zora, are you available?
Yes, I'm here.
Okay, yeah, so you are presenting next, please.
Oh, okay, thank you.
Yeah. So
okay, I can present now or after Fatima?
Okay, all right. So you then you let her present and then you present next. Okay.
Okay, thank you.
Mm-hmm. Fatima, please proceed. I think you are muted. We cannot hear you.
You hear me now?
Yes.
Yes. Thanks. Then, hello everyone. I am Bouhnsouch Fatima from University of Batna 2 from Algeria. I present to you research about primordial anterior point method for linear optimization based in a new kernel function. We start by the table of content. This is now the introduction. Inner point method are well known as the most effective in solving optimization problem. This method are ensured convergence in the most problem, and moreover are have good numerical behavior. In this research, we were interested in a study theoretical, algorithmic, and numerical inner point method for linear programming. On one side, we present a primordial algorithm for anterior point, and on the other side, we are interested in type method central trajectory. We are looking for a new kernel function with a logarithmic term or a barrier term that give the best algorithmic complexity obtained so far. The problem: consider P the standard linear optimization problem as below in Formula 1. The dual problem D with associated with P is given by Formula 2, where A is a matrix and Y, S, B, C is the vector. We assume that A is a full then function and satisfy the following condition given by Formula 3. This function may be extended to positive V by Formula 4. Then the barrier function phi is non-negative. Therefore, the value of phi can be considered as a measure for the closeness of X and the pair Y and S to the mu center of P and D. In the next section, we describe how any such barrier function define a primal dual anterior point method. The iteration bound for such large update algorithm is obtained by showing that each iteration decreases phi by a sufficient amount. Then the aim of this paper is first to propose a new kernel function with barrier term. Then we present some property of this function which are important in the complexity analysis of anterior point method based on this function. We have the generic algorithm for LO, linear optimization. We conclude the algorithm in the following figure. This is the figure of l'algorithm. Then the property of the new kernel function. We study some basic property of our new kernel function, psi, and the correspondent barrier function, phi. In addition to psi, satisfy the following condition given by 5 and 6, the kernel function must be an eligible function. What's mean eligible function? Eligibility of the new kernel function. We have the next lemma to define what mean the eligibility of the new kernel function. Lemma. The function psi is eligible function is we have this 5 condition, 7, 8, 9, 10, and 11. By using the eligibility kernel function, we get analysis of the algorithm by following general schema as present in 2. Then an analysis of the algorithm. To calculate an iteration bound for large update anterior point method, we following this step. Step 1 is solve this equality to get rho of S, the inverse function of this function. Step 2, calculate the decrease of phi in terms of delta for the default state size alpha bar from this formula. Step 3, solve this equality to get delta of S, the inverse function of psi of t. Step 4, derive a lower bound for delta of V in terms of V of V by using the formula. Step 5, using step 3 and step 5 and step 4 to find in positive gamma and beta, then we find this formula. Step 6, calculate the uniform bound for the total phi 0 for phi of V from this formula. Step 7, derive an hyperbound for the total number of iteration from this formula. Step 8, and the last one, set tau equal big O of n and theta equal big theta of 1, so as to calculate an iteration bound for large update IPM. This is what we need. Then conclusion. In our work, we propose a primal dual anterior point algorithm for linear optimization based based on a new kernel function with an efficient logarithmic barrier term. We show that the algorithm has complexity result for large update method. As consequence is this formula. The total iteration bound become big O and this formula here. Respectively, these are the best no complexity result for such method. This is some reference. And thank you for your attention.
Thank you, Fatima, for your presentation. So any questions? Any questions for Fatima? Okay, so then, so if there are no questions, then we move to the next presentation. Thank you, Fatima, once again for your presentation.
Thank you very much.
For the next presentation, we have Icheku Utade presenting next. So Icheku, if you are ready, please, you can share your slides and start your presentation.
Hello. Can you see my screen now?
Yes, we can see your screen.
Okay. Okay. Can I go ahead?
Yes, you can. Mm-hmm.
Okay. Good afternoon, everyone. I want to appreciate the organizing committee for giving me the privilege to present a paper in this conference, Ghana Numerical Analysis Day. So I'll introduce myself formally. My name is Otaide Ikechukwu Jackson from Mike University, Nigeria. I'm here to talk on numerical solution of ninth order boundary value problem. Ninth order boundary value problem using the variational iteration method with Bestin's polynomials as trial function. So in this paper, the numerical solution of the ninth order boundary value problem was obtained using the modified variational iteration method with Bestin's polynomial. So the proposed modification involves constructing the Bestin's polynomial for the given boundary value problem and using it as the approximations basis function, or what we'll call the trial function. So for the introduction, we consider the generalized boundary value problem of the form and order with boundary conditions. So for this work, many researchers have worked on boundary value problems using various numerical methods over several methods, several numerical methods discussed in the literature. We have the Galeckin's method of weighted residuals, and we also have hybrid improved cause and testing function. So other works we've done as well. We have the motivation method. So we consider what we call the standard variational iteration technique. So if we consider the following general linear differential equation, you see where will be the linear operator, L, which is a non-linear operator, and G of X, which is what we call the forcing term of the differential equation. So here we also have what we call our correction functional. So this is called as equation 4 is correction functional, where lambda of t is called the Lagrange multiplier. So in this method, what we need to do is to determine the Lagrange multiplier optimally. And we can see the definition of the Lagrange multiplier in equation 6. Minus 1 raised to the power of n, 1 over n minus 1 factorial t minus x raised to the power of n minus 1. So that's the definition of the Lagrange multiplier for any problem considered. So here we see the Besson's polynomials, of degree n minus 1 is defined as this, as you can see in equation 7, where g of I n minus 1 of x is defined as this. And this term here is called the Besson's coefficient, or what we call the Bezier coefficient. So for this work, we consider a few Besson's polynomials, and as you can see from B0,9 and we have to B5,9, few Besson's polynomials that are required for this research work. So using 3 and 4, we assume an approximate solution of the form. We consider approximate solution. Here, this is the Besson's polynomial, and so this approximate solution is equation 9. So this is the reconstruction, as you can see, reconstruction of the variation technique using Besson's polynomial, which is obviously the methodology for this work. Here we see our Lagrange multiplier. And it's almost like the correction functional, but the first thing here is replaced with the basis function or the approximate solution. So what we do next is to take an example and see how this whole thing is done in application. So example 1, we considered a 9th order boundary value problem from -1 to 1. With boundary conditions, and you can see here is the exact solution of the system. So what we do first, the correction functional for the boundary value problem 11 and 12 is given as this. So this is the correction functional, and you can see our Lagrange multiplier. It's the Lagrange multiplier. So this approximate solution. You can see equation 15, it's approximate solution. So hence we get the following attractive formula, which is a methodology which was displayed in the previous slide, not quite long. So you see this, the attractive formula, and there you can see the Lagrange multiplier. So this is the approximate solution, and this is, we call this equation system. So this attractive formula is called, we name it equation system. So on the next slide, this system is broken down. This approximate solution is broken down from I equal to 0 to 8, as we can see, 0, 8, 0, 8, 1, 8, 1, 8. So, and we call this equation 17. So as a result of 8, what's our 8? 8 is our Besson's polynomial. The few Besson's polynomial listed for this work, and applying the boundary conditions 13 for this particular problem, we get the values of the unknown constants. As you can see, A08 to 88. So, and when consequently, when this after getting this constants, when put back into the solution, it gives us what we call the series solution of this problem. So this is the series solution of the problem considered. All these things actually are done using Mapo 18 software to generate the solution. So on the next slide, there's another example here, but with boundary condition, with interval from 0 to 1, and you also have the exact solution for the problem. But time will not permit us to solve this because we've already shown the methodology from the first example. So what we do, we see the table 5.1, and this is the table generated from the first example. And the series solution got in, as you can see, this is the table, and these are the sample points considered from x equal to 0.1, 0.2 down to 0.9. This is the exact solution of the system, and this is the approximate solution gotten from these sample points. And this is the absolute error by the proposed method. And this is the method we are comparing with PGM. We call it Petrov-Galeckin's method with quintic B-splines. So this was the absolute error from that method, as we can see. At x equal to 0.1, the error gotten from our method, you can see -11, and we can see 0.7, which means our method is better. And obviously, we can say our method converges better than the method in literature. So as you can see, 7.11, 7.10, 6.9, and so on and so forth. When we compare, we discover that the method in use, or what we call the proposed method, is better than the method used by Petrov, used by Kasi, Vishwanathan, and Reddy. So the next 10 slide, we see the other table from example 2. We see the other from example 2, and we discover that our method is still far better than the method in literature. As you can see, these have 0.5, this is 10. So we see that our method converges better, far better than the method in literature. So it's, you can see the sample points considered, so from 0.1 to 0.9. So we see 10, 10, 10, and so on. You see our method here is far better than the method used in literature. We're talking about collocation method with quintic B-splines. So the absolute error gotten from our method is far better than the method compared with literature. So on the next slide, we can see a graphical representation of comparison of approximate and exact solution for the first example. This is a graphical representation. You can see you hardly find a slight difference between the approximate and the exact solution, where the orange color denotes the exact solution, and the dots here represents the approximate solution on the curve. So this is the graphical solution comparison between the exact and the approximate solution for example 1. Then for example 2, we also have the graphical comparison of the approximate and the exact solution for example 2. So in conclusion, we see that the modified variational iteration method with Bestin polynomials was successfully applied in this paper to obtain numerical solutions to 9 other boundary value problems. So Bestin polynomials and the variational iteration method are used in this in the modification. So in linear cases that occur in physical problems, the method provides rapidly convergent series solution, as we see from table 5.1 and table 5.2, as well as the pictorial representation or figures represented not quite long. So this also shows that the proposed method outperforms other methods in literature. So finally, what do we say? We say that the numerical results demonstrated that the current method is a powerful mathematical tool for solving the class of problems under consideration. So these are my references. These are also my references, and also have these as references. Also references used for this work. Thank you.
Yes, excellent. So yeah, thank you for your presentation, Ikechukwu. You know, any questions for Ikechukwu? Yeah, so Ikechukwu, I have a question for you. So did you also consider the CPU time, you know, for...
Sorry, I didn't get that.
I said, did you also consider the CPU time, the running time for both, you know, methods? Okay, in terms of like how long it takes to run, you know, did you also consider that?
Okay, if I may understand the question, you're talking about the running time for both methods.
Yes, exactly. Yeah, so because, I mean, according to your accuracy, the error, yes, the error, your method was performing better. Okay, but did you also consider the running time, the CPU time, you know, for both techniques? Which of them, you know, converges faster?
Okay, that's actually I didn't consider the same way.
Okay, so okay, maybe I think maybe that's something that you might also want to consider. Okay, whether the time it takes to converge, you know, it's maybe your method is faster, or you know, so it's good if you can do that as well.
Okay, does that have anything to do with the software?
Maybe, yeah, we can talk about that later, you know, but
okay, that's
yeah.
okay. That's
Good.
okay.
Any other questions? Okay, good. All right. So then if there are no questions, then thank you, Ikechukwu. Thank you so much for your help.
You're welcome.
Okay, so next on the list is Johnson Adikule. So Johnson, if you are here, please, you can share your screen and start your presentation. Johnson, are you here? Johnson?
Okay.
Okay, so I guess Johnson is not here. So Fatima?
Yes.
Yes, please, you can share your screen and start your presentation.
Yes. Hello. Okay, can you see the screen?
Yes, we can see it.
Very good. There I am. Okay, first of all, I want to thank you for the organization of this interesting event. I present myself. I'm a PhD student at the University of Tlemcen in Algeria. I wanted to share with you the results obtained in the field of mathematical modeling in biology. This is a recently published work with my supervisor, Mr. Mohamed Tariq Tawla and Mr. Jilali Saleh. Okay. As a motivation, let me say the world witnessed a huge increase in the number of newly discovered diseases. We mention as example HIV and COVID-19, which makes a necessity to increase the scientific contributions for stopping the spread of these contagion diseases and protecting our community from the outcome of this spread. There are many ways for limiting the spread of these diseases by making, for example, vaccines and treatments. Where a new vaccine or treatment is developed, it is very tough to make it available to the whole population due to its expensiveness and scarcity. Okay, Then we use the mathematical modeling to predict the results. Okay, the mathematical prediction is one of the best tools for anticipating the cost of the specific strategy taken by the government. This tool can be helpful in avoiding measure of resources and treatment, as treatment and vaccines. Okay, starting by defining an epidemic. What's an epidemic? It is the rapid increase of a disease in a given place at a given time. If the disease spreads rapidly to a large part of the world, it is called a pandemic. Okay, let's build our model. Consider a mixed population. Now we make a classification of its individuals according to their health situations. Okay, the class, we consider the class of susceptible individuals who are sensitive to the disease, not infected but sensitive. The class of infected people, and the class of protected people. Okay, if we denote the S as the density of susceptible individuals, S of T represents the density of susceptible individuals at time T. The I represents the density of infected people at time T, and P is the density of protected individuals at time T. The functions gamma S, gamma I, and gamma P are respectively the death rates of protected, susceptible, and infected people. The A is the entering people into the S class. The mu is the rate of recovering. Alpha is the possibility to return again to the class of protected. And K is the rate of losing protection. Okay, the H is a function which represents the rate of protecting. Beta I is the transmission rate. Now, if we consider the period spent in the class of susceptible people, we denote by AS the age of susceptibility, the AP the age of protection, and AI the age of infection. Finally, this is our model. Okay, with initial conditions. Now we make these assumptions to be able to do the study, the mathematical study of these equations. Okay, firstly, I can say that we used the fixed point theorem to prove the uniqueness and existence of solution. Now, the PDEs of system 1 can be expressed by Volterra equation as the following, using the characteristic method. Okay, we have a theorem which mean that there is a compact set which attracts all solutions of our model. Now we search to find the total trajectories. The system of total trajectory is given by this system, and remark that total trajectory means that the t is real, not only non-negative, as in the first Volterra equations. Okay, another result, our system has always trivial equilibrium expressed as the following. As you see, if you remark, the components of infected people equals to 0. There is no disease, the free disease equilibrium. Now we can define the rate, the basic reproduction rate R0 as the following. This is the expression of R0. Okay, theorem assume that R0 is little or equal than 1. The disease-free equilibrium E0, denoted E0, is globally asymptotic, stable in XY. X plus is our functional space. How to prove this result? We proposed the following Lyapunov function V of t, defined by the sum of integrals and the convex function h. Okay, the purpose is to show that the function v, or the derivative of v, is non-positive. Then we need to calculate the derivative. The derivative of Lyapunov functional need a lemma. Okay, because our solutions are not regular, and we need this lemma to calculate the weak derivative. Finally, we see that we proved that the V prime is non-positive, and using theorems we prove that the global stability of the trivial equilibrium. Okay, now if R0 is greater than 1, there exists another equilibrium which is positive, denoted EE, the endemic equilibrium, given by this expression. Okay, another theorem of stability. If R0 is greater than 1, the EE is globally stable in a compact, an appropriate set which is compact. We proposed the following functional of Lyapunov, and the same thing, the derivative is computed using the lemma of derivation. And we have also proved that the derivative of Lyapunov functional was non-positive. We propose some numerical simulations. This is the case of R0 is little or equals to 1. Then the solutions converge to the trivial equilibrium. And the other case of R0 greater than 1 and the solutions converge to the endemic equilibrium. These are some references. Thank you so much for your attention.
Okay, yeah, thank you, Fatima, for your presentation. So any questions for Fatima? Okay, so Husseini, please, you can unmute yourself and ask your question.
Thank you for giving me the opportunity. I would like to know the doubling time and the half-life of that particular model. Doubling time and then the half-life.
Yes.
Fatima, yeah.
I can see you. Yes.
The doubling time.
The doubling time and the half-life of your model.
Yes. Please, I can't hear you, please.
He's asking for the doubling time and the half-life of your model, the model that you are proposing. Did you hear the question? Hello, Fatima, can you hear us? Hello, Fatima.
Yes, yes.
Yes.
Can you hear me?
Yeah, we can hear you. Yeah, so Husseini, can you please ask your question? Maybe you can throw more light on your question, you know.
Yes, my question is on the doubling time and then the half-life. If it is a pandemic, then we should be able to estimate when the number of cases can double if care is not taken. Then also if we are handling it, when we can reduce it to half of its value, the possible time. So I just want to know if that has been catered for in the model and the clarifications on that.
Okay.
You
Fatima,
mean that how to make the R0 increasing? I didn't. I hear the half of the question. Please, can you repeat?
I think I'll communicate to her at the background so that she will help me out.
Okay. All right.
Thank
good.
you.
No, you're welcome. Okay, so I have another question. Danani, yeah, please unmute yourself and ask your question.
Okay.
Danani. Danani? Okay, so any other questions before we proceed? Any other questions? Okay, good. All right, so the next, so then thank you for your presentation, Fatima. Thank you so much. Okay, we appreciate it.
Thank you.
Yeah, good. Good. So the next presentation is Mohammed Shimi. So Mohammed, please,
Yes.
you can share your screen and then give your talk. Ikechukwu, do you have any questions? I see your hands raised. Do you have any question?
Okay, yeah, actually, I actually wanted to talk to you. Can you hear me?
Yes, I can.
Okay, I actually do not have a question for for Fatima's presentation, but I just want to give an answer to the question you asked during my presentation. I think the running time is 1:3. In the work I compared with, they did 3 iterations, but I did just 1 iteration. So the first iteration gave me that result.
Okay, all right, okay.
Thank you very much.
No, you're welcome. Okay, yeah, so Mohammed Shimi, please, you can start your talk.
Okay, thanks. Hello, everyone. First of all, I would like to thank the organizing committee for this opportunity to present my work entitled on a non-local problem with variable exponent. So I will follow the following plan. In the first section, I will give an introduction in which we present the motivation and statement of our problem. In the second section, I will introduce the fractional subgroup space with variable exponent, and in the last one, I will establish the existence of solution for fractional px Laplacian problem via Nehari manifold approach. So we define fractional Laplacian operator by its usual model notation given by the formula. It is the most famous operator in the family of non-local operators, where CNS is a dimensional constant that depends on n and s. Precisely, it is given by this expression. For symptotic behavior, we have that the fractional Laplacian operator tend to the classic Laplacian when s tend to 1 minus, and it tend to identity when s tend to 0 plus. This operator has 10 equivalent definition. The first one is given by the Black-Richman formula. Second one by Fourier transform and distributional approach. Also, it can be defined by singular integral, Bochner definition, also Dinkin's definition, quadratic definition, and also it can be defined by semi-group approach, harmonic extensions, finally by the inverse of as an inverse of the Ritz potential. So as you see, this operator we have different type of definition, so it varies in a quite natural way in many different contexts of applications, such as the phase transition, also in stratified materials, and also in the water walls, in the geophysical fluid dynamics, and in the anomalous diffusion. There are other area of applications such as the conversation laws, minimal surface, population dynamics, mathematical finance. Also, the fractional Laplacian provide a simple model to describe certain jump Levy processes in theory of probability. This operator can be extended to the nonlinear case, normally for p belong to 1 plus infinity and u a smooth function. We introduced the fractional p Laplacian operator. So as a question, what happened in the case of the fractional or in the case of the variable exponent? On the one hand, we have in the constant case we have the fractional Laplacian operator. On the other hand, in the case of a variable exponent, we have the classical Laplacian, the px Laplacian operator. So if we combine the definition of these two operators, we obtain fractional Laplacian operator defined by this formula, where p is a symmetric continuous exponent function and s belong to 0, 1. Now, we give the statement of our problem. So we are concerned with study of existence and multiplicity of non-negative solution for a fractional Px Laplacian problem with directly boundary data, which is given by problem Ps lambda W. As you see, we have the presence of the operator, the Px Laplacian operator, and two weighted function W1 and W2. Here omega is a Lipschitz bounded domain. S belongs to 0, 1. Lambda is a positive real number. And P, Q, R are three bounded continuous functions which satisfy following inequality. Inequality number 2. So we assume that W1, W2 are two continuous non-negative weighted function on omega bar satisfied following assumption. So the first one is W1 and the second one is W2, where alpha, beta, QR belong to C plus of omega. Now we will present the functional framework in which we will study our problem. We start by the diagram of the functional framework. We have for the first instance the Lubick space in the classical case, also Sobolev space, classical Sobolev space. So these spaces are defined in the case of integer derivative, and for the fractional derivative we have the Holder-Zygmunt space. If we combine those three spaces, we can introduce fractional Sobolev space. Lubick space and Sobolev space were extended to the general case with variable exponent. So if we follow the same approach, we can introduce fractional Sobolev space with variable exponent and its general case with a symmetric singular kernel. So we assume that omega be a Lipschitz bounded open set inner N. P is a continuous bounded function and which satisfy the assumption 3 and 4. And we set P bar of x equal a P of xx for all x belong to omega bar. Then we give the definition of fractional Sobolev space with variable exponent as follows. This space is endowed with the following norm, with this quantity is the Galliardus semi-norm with variable exponent defined by this expression. Our space X equipped with his its norm is a separable reflexive Banach space. For U belong to X, we define the modular function given by this expression and its associated norm given by this formula. So we move now to the continuous and compact impending results, which are very important in the study of our problem. So if we assume always that omega is a Lipschitz bounded domain, S belongs to 0, 1, P a continuous variable exponent which satisfies the assumption 3 and 4, and R is a continuous variable exponent satisfy this inequality, then the space X is continuously embedded in LRX of omega. Moreover, this embedding is compact. The same result, we can obtain the same result, that is same result for the white Lubick space if we assume that W1 is verified. So X is compactly embedded in the space of in the Lubick space LQX omega 1 of omega. And also F omega 2 verified. So we have also the same result We have the contact independent of X in LRW2 and the modeler satisfy those two inequality, the inequality number 5 and the inequality number 6. As a consequence of the above result, we have this inequality for the modeler of row QW1 and row RW2. Now we can study our problem. So to apply Nihari manifold analysis for our problem, we consider the energy functional phi lambda associated to our problem defined by this expression. In general, in a lot of problems, phi lambda is not bounded on the whole space X, but it is bounded on appropriate subset of X. So a good candidate is the following subsets of X associated to phi lambda and defined by this formula. So in the assumption of theorem 2 and if the inequality 2 holds true, then functional phi lambda is coercive and bounded below. Moreover, phi lambda is of class C1 on X, and its Gatto derivative is given by this expression. Now, if the derivative of phi lambda on U equals 0 and U different to 0, then U belong to N lambda. So N lambda is the natural constraint for the problem of finding non-trivial critical points of phi lambda. If we set C equal the infimum of phi lambda on N lambda, under the assumption of our problem, one hopes that C is attained at some U0 belong to N lambda and that U0 is critical point of phi lambda. Now we consider the function psi defined from N lambda in R by following formula. Hence, it is natural to split our subset N lambda to three parts. The first one is corresponding to local minima, and second one to local maxima, and third one corresponding to the point of inflection, which defined respectively as follows. Now, to get non-trivial critical point of phi lambda, we follow this scheme. In the first step, we prove that in lambda 0 equal empty set, which implies that in lambda equal the union of in lambda minus and in lambda plus. So if we assume that the assumption 2 and the assumption of theorem 2 are satisfied, then there exists lambda star, positive constant lambda star equal, such that for any lambda belong to 0 lambda star, we have that in lambda 0 equal empty set. In the second step, we show that sigma lambda minus, which is the infimum of lambda on in lambda minus, and it is positive, and the infimum of phi lambda in n lambda plus, it is negative. So if we assume that the assumption of theorem 2 are satisfied, then there exists lambda star strictly positive, such that sigma lambda plus is negative, and there exists also sigma lambda 2 star strictly positive, such that sigma lambda minus is strictly positive. Then in the third step, we deduce the existence of E0 lambda, E0 plus belong to N lambda plus, and E0 minus belong to N lambda minus, such that phi lambda of E0 plus minus equal the infimum of phi lambda on N lambda plus minus. So if we assume that assumption 2 and assumption of theorem 2 are satisfied, we can find a lambda star For all lambda belong to 0 lambda star, there exists a minimizer E0 plus of phi lambda on n lambda plus, and also we can find a minimizer E0 minus of phi lambda on n lambda minus, such that E0 minus phi lambda of E0 minus equal sigma lambda of sigma lambda minus. As a conclusion, now we are suppose that omega is a Lipschitz bounded open domain in Rn, and S belong to 0, 1, P belong to C plus of Q bar, which satisfies the assumption 3 and 4 on Q bar with SP plus, with N greater than SP plus, and we assume also that assumption or condition 2 W1 W2 hold true, then there exists E0 E0 minus plus belong to n lambda minus plus, such that this E0 minus plus is positive, and phi lambda of E0 minus plus is the infimum on n lambda plus. Consequently, since n lambda 0 is the empty set, it follows that n lambda minus intersection of n lambda minus and n lambda plus is the empty set. Then E0 plus and E01 are two distinct critical points of phi lambda, and hence there are two non-negative weak solution of our problem. There are some references in which I passed my work. And thank you for your attention.
Thank you, Mohammed, for your presentation. So time for questions. Anybody has a question for Mohammed? Any questions for Mohammed? Okay, good. So if there are no questions, then thank you once again, Mohammed.
Thank you very much for you.
Okay, you're welcome. Good. So next is Johnson Adekunle. So Johnson, are you available to present? Johnson? Okay, so I guess Johnson is not available. He's not online. And did we miss anyone? Is anybody supposed to present that we've missed him or her? Did we miss anyone? Okay, all right. So then I guess then we've been able to accomplish our task today, and unfortunately Stephen is not with us, but maybe a couple of announcements. So first of all, I would like, on behalf of the organizing committee, I would like to thank each one of you for taking time out of your busy schedules to join us, and also for sharing it with us, your interesting research. I think it's we've all learned a lot. Okay, and I feel that we've built the network and connections for collaborative work. Okay, so I think that's something which is very, very good. And then let me share my screen. Okay, let me share my screen whilst so give me 1 minute. Can you all see my screen?
Yes.
Okay, good. Yeah, so the cool thing is that for this workshop, okay, we've partnered with the publishers MDPI, for a special issue called the Ghana Numeric Analysis Day. Okay, so you have the option to submit your talk or the research as a special issue in the journal Mathematical and Computational Applications. Okay, so I would highly recommend that you do that. Okay, so the deadline for you to submit your manuscript is on December 15th. Okay, that's the deadline to submit your article. So I will highly encourage all of you, those who presented, to submit your talk to this special issue. And the cool thing is that it's free of charge, so once you presented your work, you don't have to pay for it. Under normal circumstance, the charge is about 1,400 Swiss franc, which is, almost 1,600 US dollars. So then if you get to submit your work free of charge, I guess it's a win-win. One, you've been able to present here, and also you get an option or the opportunity to present your work free of charge. Okay, so please, let's do that. Okay, so once I'm going to share the link. Okay, I'm going to share the link in the chat box. Okay, so let me do that right now. Okay, so I have posted the link in the chat box. Okay, so let's all take advantage of this great opportunity. Okay, let us take the advantage of this great opportunity. Just in case, if maybe you want to come back, so this is the Ghana Numeric Analysis, website. So once you come to the website, then we also have the link also here. So you can always, revisit the link in the future, just in case you miss it. Okay, you can always revisit it. So you go to the Ghana Numeric Analysis page, and then you can obtain it. So let me stop sharing. Yeah. So any questions on the publication? Any questions or concerns? And I believe, since it's the last period, can we all put on our cameras? If we can. Okay, so we can all see our faces, and then maybe if we meet somewhere, it could be in person, or it could even be at another conference, we can acknowledge one another. Yeah, so any questions on the publishing? So I think it's a win-win for all of us. Okay, so let's take advantage of this great opportunity. Right, good. Any questions or concerns? Okay, so if there are none, then maybe what I want us to do is I want us to take a group picture. Okay, and then we'll share with all of us. Okay, so unfortunately, some of our colleagues have left the line, but then all those present. Okay, okay, before we take the group picture, Ikecheku has a question. Yeah, so please go ahead.
Can you hear me? Hello, can you hear me?
Yes, we can hear you.
Okay, I want to sincerely appreciate the organizing committee for putting up a conference like this, Ghana Numeric Analysis Day. It's a wonderful one, and I want to say kudos to the organization committee and Ghana as a country setting up a day like this. So what I want to ask is that apart from papers being presented that will be published free, is it possible for one to send a paper not presented for publication?
Okay, yeah, so the whole idea is that it's a special issue geared towards the Ghana Numeric Analysis Day, right? So then preferably we want all papers submitted to be talks that were presented in this conference. I understand that there could be some variation, okay, but preferably we want all talks to be all papers to be talks that were presented on this.
Okay, only papers presented should be published.
Yes, correct.
Oh, okay, that's okay. Thank you very much. Once again, I appreciate it.
Oh yeah, and also one thing is that so this is a yearly workshop. Okay, so next year hopefully we will also have another workshop. Okay, so please spread out this information to your colleagues or friends. Okay, that this is a yearly workshop that we organize. So yeah, so that's something I also want to mention. Any other questions or concerns? Okay, and I guess some of us were able to introduce ourselves yesterday, others could not. Okay, so if you were not able to introduce yourself yesterday and you are here today, can you please let us know your name, you know, where your affiliation, and maybe some of your research interests? You know, we have about you know, I'll put it maybe about 20 minutes. Okay, so let's use that time to, you know, interact, get to know one another, and then even share or exchange email addresses. So Michael Poby, you know, yesterday, were you here? Were you present yesterday?
Yes, I was.
Oh, okay. So were you able to introduce yourself? You know, maybe if you don't mind.
Okay. I'm Mike Poby from a PhD student at University of Cape Coast. And I'm also doing a mathematical modeling in epidemiology.
Okay.
Yeah, at UCC.
Okay, excellent. And I guess, you know, for most of the work, I would say that about half of the presentations were geared towards mathematical modeling of, you know, epidemiology. So I guess, please, you know, feel free to, you know, direct message, you know, the talks that are of interest to you and exchange, you know, emails. Okay, please do that. It's very important that we build that connection and then build that network. It's very, very important. Who again was unable to introduce himself yesterday? Fatima, do you want to introduce yourself? Because I think yesterday you are not present, you know, Fatima Zura.
Yes. Hello.
Yes, hello.
Can you hear me?
Yes, we can.
Okay, I'm a PhD student at the University of Tlemcen in Algeria. And I work in the domain of mathematical modeling in biology.
Okay, okay. Excellent. That's good. So like I said earlier on, I think Fatima has, you know, reconfirmed my stance that majority of the people here are in mathematical biology. So please,
yes.
You know, feel free to exchange emails. It's very important. Yeah, so I think there was a question from Husseini. How long will it take for the journal to publish the work? Well, it's relative. Okay, so usually the turnaround is, you know, it's about, so once you submit your work, they will send your work to the reviewers. Okay, so it's all dependent on how the time it takes for the reviewers to submit their review. Okay, so it's relative. So I would say that within a month, okay, if assuming that you are able, I mean, you are very fast, and then if there are any changes, or if they recommend any changes, you are able to accommodate and perform all those changes, then your work should be published within a month or two. Okay, so it's relative. I cannot give a you know, a definite answer time frame, but then it's really very fast. Okay, so Mohammed, what do you mean by attestation? Can you please clarify that? Mohammed? Or are you mentioning certificate of participation? Is that what you are referring to? Iketeku, you have your hands is raised. Do you have any question again?
Yeah, I have a question.
Yeah, please go ahead.
Yeah, with regards to the certificate of participation, you know, we had some not really an issue anyway, but we're trying to contact the organizers and telling them that the names of our corresponding authors were not appearing in the program. Can you hear me?
Yeah, we can hear you. Yeah.
So we appealed to them to include their name in the program. That is to say, when certificates have been awarded for presentation, the corresponding authors should also have their certificate. I don't know if that has been put in place.
Okay,
maybe I can answer this one.
Yeah, please go ahead. Okay.
If your co-authors did not register to attend the workshop, then they will not have their names in the registry as participants because they did not participate. If you participated and you presented a paper where your co-authors' names are in the article, it doesn't mean your co-authors are also participating in the workshop. So even if a certificate is issued, your co-authors will not get a certificate for participation. It is only the person who registered to participate. And even now, even the people who may get will be those who probably are online. I'm not even discussing.
Okay.
So, yeah. If you have a paper which is co-authored or presentation co-authored by 10 people, then it doesn't mean that all of them should be participants. So this is what I mean by if your co-authors did not register, then they cannot get anything that one person cannot represent 10 people for a conference or a workshop.
Okay, can I ask another question? Can I ask a question?
Yes, please go ahead.
Okay, I understand what you've said. But what about if my co-authors they participated in the conference, as in they were online in the process, they attended the conference online? Would they be issued certificates? Would they issue certificate to them? I don't know if you get the question.
You know, I think Stephen made it clear that in order for you to, obtain certificate, there's two things. First, you need to register. Okay, that's the first thing. That's the first requirement. You register and then you present. Correct? So now the question is, what if you did not, present? If you did not present, but then you were online for the presentation, for the whole duration of the talk, then yes, you get a certificate.
Okay, maybe you don't understand what I'm trying to say. What I'm saying is this. Actually, when I made a complaint to them, to the organizing committee, the person made the same statement. That means they did not register. So the person later said that I should resend the abstracts to them. Are you there? Of which I did. I sent the abstract to them and an appeal also. So I wouldn't know if my co-authors registered, but they attended the meeting for today, the conference for today. So that so what I'm saying is that I am the one that registered. I am the one that represented. So my question now is that they attended the conference online today. So now that they attended the conference, my question is, will they be given certificates as well?
And yeah, so unfortunately, no, because that's the solution. First, you need to register.
That means all of them need to register. They would have registered, all of them.
Exactly. Yes.
Okay.
Yeah. So then maybe what will benefit them is that when you submit the paper for publication, then yes, your name are going to be there. Okay. But then for the certificate of participation, the first criteria is that you should register for the workshop.
Wow. Okay, maybe my own contribution to this is that maybe for next time, maybe you should specify on the site that all corresponding authors must register, because it was not stated there. Maybe that's why they feel it was not of necessity for them to register. So maybe they think it's only the person who is presenting the paper that should register. I don't know if you understand what I'm trying to say.
Okay.
Like,
Yeah, fine. Okay. Yeah, we understand that. Okay.
Yeah, it was not spelled as in capital letters that the corresponding authors should register.
Okay,
Yeah?
sure, no problem. Yeah.
Yeah, like we have been attending conferences, some in Turkey, like that. So when I present the paper, my corresponding authors get certificates. They don't even attend, but they get the certificates. So how much more this one that they attended, the only problem is that they did not register. So I'm thinking we should just beat it down a little bit.
Yeah. So we will take that into account.
Please, especially now that in the website it was not stated categorically that the corresponding authors should register. So I'm thinking we should just it's an appeal anyway. It's an appeal for the first time is to encourage them to. Because some of them they attended this conference today because I'm presenting today. We are presenting our paper. So I'm thinking maybe we should just
I understand.
put them into consideration.
Yeah, I understand. Okay. Yeah. So Oyedepo, do you have a question? Oyedepo, your hand is raised. Do you have any question?
I can hear you. Just tell him to unmute himself.
Yeah, unmute yourself. I think you're muted.
Can you hear me?
Yes, we can hear you now.
Yes, I said in line with the question that Mr. Eke asked now, that if your co-author also conference, if your co-author also presents this conference, will you give them a certificate of presentation?
Your line was breaking. I couldn't hear you clearly.
Okay, I said, if the co-author also presents in this conference, will they be given certificate of presentation?
Yes, I mean, if they present, so first, did they register? If they registered and presented, then yes, they will receive it.
All right.
Yeah. Good. Any other questions? Okay, so then if there are no further questions, then please let's take a group picture. So I'm going to take a screenshot. So if you can, please kindly put on your camera, okay, and then I'll take a picture, and then we would end our call. Okay. All right, excellent. Okay, good. So we will share the picture with all the participants. Okay, so thank you once again, and we look forward to see you guys maybe in person, virtually, or next year. Okay, so thank you for taking time to be present today. All right, okay. Have a good one.
Yeah, thank you too.
What do you say?
So thank you too.
Okay, no, you're welcome.